So in this video, we're going to continue to evaluate whether a series converges or diverges. In this one, we have 1 over ln n to the power of n. Again, every time we have a ln n, we're going to apply the integral test and say that 1 over ln of x to the power of x from some constant to infinity dx. We're going to make a u substitution. U equals to ln of x, and eu du equals to dx. See the previous video if you want to know how I got this differential. And then we're going to substitute it back in. So ln of k to infinity 1 over, well, it's not 1 over anymore, it's e to the u over e to the, not e, u to the power of e to the u. Oh, well, this is a bit of a hassle. Okay, so I don't know what's going on with this, function. What I can do is I can ln everything and put it to the power of e to the u. So if I say e to e, or in the short form for that is exp, so the exponent of, and we have ln of e to the u is just u, and ln of u times e to the u is e to the u ln u. Okay. And since we know, and I guess we'll put an integral here, du. What we know about the series as, so let's actually convert this back to a series of sum of n equals b to infinity of the exponent of u over e to the u ln u. This would fail our divergence test because e to the u is a larger number than, a larger number than u. No, this is not u. We're counting from n. Sorry. N over ln n. So from here, what would we do from here? From here we would say, well, much like a limit, if we can prove that, because e is a constant, if we can prove that this portion converges, then e to some converging number will also converge. So instead of evaluating this, we're actually just going to evaluate n equals b to infinity of n over en times ln n. At this point, I'm going to use a ratio test, limit as n goes to infinity of n plus 1 over n, en over en plus 1, ln n over ln n plus 1. This term goes to 1. The first term goes to 1. The second term goes to 1 over e. And the third term, ln n over ln n plus 1 by law Pt2 rule, becomes 1 over n plus 1. So this also goes to 1 as n goes to infinity. It's to 1 over e. Which means that, which is less than 1, which means that the series converges. If the series converges, then e to this number will also converge, which means that this integral converges, which when we go back means this integral converges, which means our original series converges. So this converges. There was a lot of steps to get there, but that's one of the things about these convergence tests. Sometimes you have to use more than one of them to find whether a series converges or not. This next one is quite interesting. So the sum of sine 1 over n from n equals some constant to infinity. This one we kind of have to recognize as n gets really large, 1 over n actually becomes a really small number. And if we remember this identity, limit as n goes to 0 of sine n over n is actually equal to 1, because as n gets really small, the n and sine n becomes approximately the same number. So actually, not n. Let's use a different value, like b. B. And now in our case, if we let b equal to 1 over n, then as b goes to 0, 1 over n goes to infinity, which means we have a limit as n goes to infinity, yes, as b goes to 0, n goes to infinity, of sine 1 over n over 1 over n. And this equals to 1. And this looks an awful lot like the limit comparison test, because in fact it is indeed the limit comparison test. So we can say that sine of 1 over n has the same behavior as 1 over n as n goes to infinity, because it has a factor of 1. And since we know that the sum of 1 over n diverges, because it's a p-series, or with p equals to 1, or it's just a harmonic series and you know it diverges, we can say that sine of 1 over n also diverges.